Good morning, class. Here's exam 2 review covering chapter 3 from 3.1 to 3.8, part 2, 3.4, and 3.5. You're looking at the chain rule and implicit differentiation. So speaking of the chain rule, how can we differentiate composite functions such as y equals square root of 10x, square root of 10x plus 5, or f of x equals 10x squared minus 1 to the power of 50? We use the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x. So we say the derivative of f of g of x is f prime of g of x times g prime of x. It is important to understand f is the shell function, the outer function. So you differentiate the outer function with respect to the g, and then by the chain rule times the derivative of the inside g prime of x. If we go with the Leibniz notation, where y is a function of u is a function of x, we write dy dx is dy du times du dx. That's the meaning of that. Now, we will elaborate on all of them as we go through examples. So, in short, when capital F represents the composite function f of g of x or f of g of x, then capital F prime is the derivative of f of g, which is f prime of g of x times g prime of x. As an example, we remember the power rule says the derivative of x to the power of n is n x to the power of n minus 1. This is a basic power rule. Now we're going to extend this to what's known as the general power rule, also known as the extended power rule. The derivative of g of x to the power of n equals n g of x to the power of n minus 1 times g prime of x. What I want to add here quickly is this. First and foremost, this general power rule, also known as extended power. The second thing I want to add, I want to look at the basic power rule. If you look at this function being raised to the power of n, what is the derivative of x? It's 1, so we don't have to write it. But g of x, what is the derivative of x, is g prime of x. So it's very similar to the concept of a basic power rule. So when a function is being raised to the power of n becomes a coefficient. The same thing to the power of n minus 1, just identical to that. However, in this case, we are dealing with x. Then the derivative of x is 1. We don't have to write it. But in this case, we are dealing with a function that we can differentiate, and the derivative is no longer 1. So we have to multiply it by g prime of x. So one way that the chain rule is understood better, if we look at this simple example where y equals sine 2x, sine of x squared, sine squared of x. So I want to show you how to differentiate that. And we need to understand that in all cases, the shell function, the main function, the outer function is the sine function. Now, one way that can make differentiation of trigonometric functions easy is the way you read it. So if I want to differentiate this, I'm going to read sine and I'm going to stop. I'm going to read y equals sine. The reason I stop, because it will help me with the differentiation, because I recognize the main function, the shell function is sine. So I'm going to write y prime is, what is the derivative of sine? Cosine. And I'm going to stop. But any trigonometric function requires an argument. This is called argument of a sine function. So you have to write the same argument. Then according to the chain rule, you have to multiply, this is the inner function, you have to multiply by the derivative of 2x, which is the inner function, and it becomes 2, and you rewrite it as such. So y prime is 2 cosine 2x. If you look at the second one, again, I'm going to say sine, and again, I'm going to pause, and I'm going to say the derivative is cosine. I look at the argument, and I need the same argument. So again, sine, pause, that is your main function, the shell function, the outer function. X squared is the inner function. You have to write that this is also an argument. So the inner function, the derivative of that is 2x, and you put the 2x in front. If it helps, the third one, you rewrite it as sine x to the second power, and you are going to use the extended power rule, n2. So let's write it. N is 2. Then g of x, or sine x, to the power of 2 minus 1, or simply 1. And then g prime, the derivative of sine x, cosine x. You write it, and some of you may remember this is sine 2x. You don't have to change it. This is fine, or you might write this is sine 2x. All right, let's continue. We want to differentiate this. Anytime you have a rational function or a fractional function, and I call this a fractional function because it's not a rational simply because the denominator is not a polynomial, and the numerator is a number, you don't have to use the quotient rule. So this is x squared plus 3 to the power of 1/2 comes up, and it becomes 4 times x squared plus 3 to the power of negative 1/2, and now I can use the extended power rule on that. So let's differentiate. Number one, we have the 4, and we are going to keep it because it's just a number that exists. Now I'm going to look at this part, and I'm going to follow this. My recommendation to you is very simple. You have to memorize the formulas. So if you're differentiating this, you have memorized the formula. Write the formula for yourself and follow it. So I am following this formula. It says n, so I put negative 1/2. Then it says g of x to the power of n minus 1. So this one to the power of the same thing minus 1. So minus 1/2 minus 1 makes it minus 3/2. So this is this part, g of x to the power of n minus 1. So minus 1/2 minus 1. Minus 1/2 minus 1 becomes negative 3/2. Finally, we have g prime of x. That means I need the derivative of the inner function, which is 2x, and I'm done with calculus. This is the only calculus step, everybody. Now I'm going to go with the algebraic techniques. 4 times negative 1/2, negative 2 times 2, negative 4 times x. I put that in front. This goes down, takes a positive 3/2 as exponent. And then I change it to the square root. So this goes down, positive 3/2, and I change it in this manner. In other words, I can write this as negative 4x, x squared plus 3 to the power of 3/2. There you have it. All right. Now I want to differentiate cosine of 3t to the power of 4. On purpose, I have used a different color to make a point, but I just went over as far as sinusoidal functions and differentiation because I've seen in the past students having a difficult time with that. So I want you to concentrate on cosine. The way you do it, you say y equals cosine of 3t to the power of 4. First, you read it that way. And then the second time, you say y equals cosine and you stop. Just cosine, stop. What is the derivative of cosine? You should know it's negative sign. So you're going to write negative sign. So you're going to write negative sign. For cosine, the answer is negative sign. But any sinusoidal function, any trigonometric function has an argument, and it must, because this is meaningless, by the way. So I use whatever the argument is here. So I must use the same argument. By the chain rule, I need to multiply it by the derivative of that. So times 12t cubed. And I'm done. All I have to do, put this in front, and this is my final answer. So in essence, if you have u as a function of x, then you have du dx. In other words, let me write this for you. If we happen to have sine u, then the derivative is cosine u, and then du dx. And by the way, if instead of u, they say g of x, then it's cosine of g of x, and this is g prime. That's the meaning of it. So we can easily extend the chain rule to a general form. All right, we want to differentiate this. And again, I want to emphasize, anytime you have a rational expression or even a fractional expression, you ask yourself, can I simplify it? And in this case, the answer is yes. If I write this as x squared over x becomes x, and this one as 4x over x becomes 4. So I don't need to worry about the quotient rule. So this gives me x, this gives me 4. And now clearly, this is using the extended power rule. So 6 sits in front, the same thing to the power of 5. The derivative of the inside is 1, and I'm done in one shot. Very simple, very fast. What about this one? If I differentiate this again, I'm going to go with the extended power rule. So the very first thing you have to use is to say y prime is n, which is 5. Then g of x to the power of n minus 1. That means whatever this parenthesis is to the power of 4. And finally, g prime of x, which means now this one, I have to differentiate and put it here by the chain rule. And to differentiate this, I need to use the quotient rule. So let's call this f over g. So again, I I recommend you memorize the formulas, then write the formulas next to you. So you wrote this formula, you wrote this formula. Now f prime g, the derivative of the top is 2 times the bottom. This is f prime g. That's the meaning of the derivative of the top is 2 times x minus 8. Now minus g prime f, g prime, the derivative of the bottom is 1 times the top, 2x plus 3, over g squared. Simply put x minus 8 here in a parentheses and square it. And this is the only calculus step. Now, before we continue, I want to make sure that if you go this route, it's a lot easier, it's a lot faster than keep on writing ddx of this, ddx of that, and sometimes getting confused as to what you mean by that. Now, the following steps are all algebraic steps, starting with simplification of this statement in the numerator, which means I'm going to have 2x minus 16 minus 2x minus 3. Clearly, 2x and negative 2x cancel each other. I end up with negative 19. Now, right here, you can go to the final step. However, to make sure that we know what we have, if you have a huge fraction bar, what is at top? 5 is at top, 2x plus 3 to the power of 4 at top, negative 19 at top. X minus 8 to the power of 4 in the denominator, x minus 8 to the power of 2 in the denominator. So I'm going to rewrite it in the following manner. So this one I write it, and this one I write it as two fractions, as two pieces. A fraction such that the top is in the to the power of 4 and the bottom is the power of 4. And this one is simply negative 19 over x minus 8 quantity squared. The reason I did that, because sometimes students, they don't know how to combine those two. This is x minus 8 to the power of 2. They take this to be x minus 8, but it's really to the power of 4. So it becomes x minus 8 to the power of 4 plus 2 in the denominator. And the top is the product of this one, and this one. The product of these two is negative 95. And this is your final answer. So I just wanted to make sure there is no algebraic mistake. All right, let's start with this, reminding everybody that the derivative of e to the power of x is itself. What is the derivative of e to the power of kx? It's itself times the derivative of the exponent, which is k. So I want to make sure everybody understands what's going on here. So if the exponent is k times x, again, you write the answer is itself times the derivative of the exponent, which is k. And since k happened to be a number, you put it in front. If you're differentiating e to the power of g of x, again, the answer is itself by the chain rule times the derivative of g of x, which is g prime of x. So let me show you how we are going to differentiate this. I'm going to say, because I see e to the power of 5t, immediately the answer is itself. But I'm not done. Anytime I see an exponential, base e, the answer is itself. Just write it down. Next, if this is t or x or theta, I'm done. But it's not. What is the derivative of that? 5. And of course, I'm going to rewrite it. Y prime is 5, e to the power of 5t. I'm writing this one. The moment I see e, I'm going to write itself, e to the power of tan x. So just write the same thing. Is the exponent x or t or theta? No. So what do you need? The derivative of tan x secant squared x. And when we rewrite it, we keep the secant squared second just the way it is. If you put it in front, you have to put a raised dot in between. Part C. First, I want to rewrite this so everybody is clear as to what we are dealing with. We are dealing with e to the power of 2/3 x, because sometimes students may be confused as to what is given. So that's algebra. I want to just make sure we understand it's 2x over 3 means 2/3 x. Therefore, y prime is itself. Times, what is the derivative of 2/3 x? 2/3, we put it in front, and we are done. All right, so it's pretty straightforward. Again, a quick recap, e to the power of x is itself. If it's e to the power of kx is e to the power of kx times k, or k times that. If it's e to the power of g of x is e to the power of g of x times g prime. And both of them, these two are by the chain rule. The moment I see a rational function or a fractional function, I ask myself, is there any way I can simplify it before I do the quotient? Because if I can't, I have to use a quotient. And again, maybe we can't, but what I want you to ask yourself is that even if the numerator can be factored, but if it doesn't have a factor of x plus 3, it's not going to do us any good. So one way, try, and I'm not saying it's going to work out, but try with x plus 3. And then since this number is a prime number, you have no choice but to have 2x and then figure out if you can factor it and what do you need there. So we can factor. Again, why did I put x plus 3? Does it factor such that it has a factor of x plus 3 always? Absolutely not. We are hoping it does, so we tried with that, because even if it has a different factor, nothing simplifies, but this does. And everybody knows the derivative is 2. So fast, you can see the answer. So again, the reason we do that, because we are hoping we can simplify. We are hoping we can simplify it. All right, we are interested in differentiating y equals 3 to the power of x. And we don't know the derivative, so I'm going to remind you what we have done. We do remember the derivative of e to the power of x is e to the power of x. The derivative of e to the power of kx is itself times k. E to the power of g of x is itself times g prime. But we never had to deal with a base which is not e. So how do we deal with that? So in other words, what if we have a general form of a b to the power of x, but not e? And we don't know that, but let us use logarithmic properties. So in this case, I'm going to remind you that ln of e to the power of x is x, e to the power of ln x is x, and this is referring to the fact that logarithmic functions and exponential functions are inverse functions. So I don't know how to differentiate this when the base is b, but if the base were e, I could use one of those rules to do the math. So the fact that e to the power of ln x is x, I can replace the b, therefore, with e to the power of ln b. This is logarithmic property, everybody, logarithmic property. So I'm going to change the b to e to the power of ln b. And please understand, ln b is a number. it is most likely an irrational number, but nevertheless, it is a number. It's like K, just like here. So I'm going to write ln b times X in essence. And again, ln b, I want you to see this. This is just like K. So this ln b is K. So the answer is this one. So the answer is itself. Now I know how to differentiate this using the chain rule. The answer is itself, and then times ln b, which is K or a number. And now this part, e to the power of ln b is b, so I'm going to put it back. So this part, I'm going to go back to b, and I'm going to replace it with b, meaning, what is the derivative of b to the power of x? Itself. Times what? If the base is e, we are done. If not, ln b. So what is the derivative of y equals 3 to the power of x? Anytime you have an exponential, the answer is itself. Then you look at the base. Is the base e? No. Then times ln 3. And you rewrite it, by the way, the reason we keep it in the same manner, because if you put this in front, one may read it as ln of 33 to the power of x. You don't want that. Now, this becomes obvious that in essence, we are dealing with the same thing and in conjunction with the chain rule. So we're going to write, if it's b to the power of f of x, the answer is itself times ln b because of the logarithmic properties times f prime because of the chain rule. So if I want to differentiate this, because I see exponential format, I write itself. So the answer is itself. Is the base e? No. I need ln b. I need ln of the base, ln 2. Is the exponent x or t or theta? No. I need the derivative of that. This is by the chain rule. So logarithmic property, chain rule, and we rewrite it in this format. I hope everybody is clear on that. Let's look at an application problem. Could somebody read this question for us, please?
I'll read it.
Thanks.
Observations show that length L and mm from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kg. Furthermore, a young tiger's weight can be estimated in terms of its age, t, in days, by the function W equals 3 plus 0.21 t.
Excellent. Thank you so much. How long is a tiger when it is 100 days old? And we have a couple of different ways to approach that. So I'm going to deal with it just the way it is. I hope you realize L, or the length, is a function of W, or the weight. Length is in millimeters, mm, and weight is in kilograms, or kg. And so if we want to come up with the answer, we have two choices. We can make L a function of t and plug in 100, or first and foremost, let's find the weight by plugging in 100. And obviously this is 21. With 3, they add up to 24 kilograms. Now that we have the weight, we are going to replace it in this formula, L equals 0.25 W to the power of 2.6. And we need to use a calculator, obviously, and we end up with this answer, 969.369 millimeters. And I'm going to remind you that 1 meter is 1000 millimeters. Therefore, it's almost 1 meter. At what rate is the length increasing when it is 100 days old? I want to make a point. The moment you hear rate, it's either average rate or instantaneous rate. In calculus, almost always we're dealing with the instantaneous rate. And how do you know it's instantaneous rate? Because 1 point in time is given. If it says what is the rate of the length increasing from to, then they give you 2 points in time. There's 1 point in time. And according to Leibniz's notation, we want the rate of length with respect to time, because it's in days, so we want dl dt. And I want to make sure everybody knows how to come up with that. So I'm going to go back to the Leibniz's notation where we put dy dx is dy du dx. So what is u? U is the intermediate variable. It's the variable that connects the y to x. In this case, L is a function of W, and W is a function of T. So I'm going to write it in this fashion. So I'm not going to put anything here. So as you can see, if you go back here and assume this is a fraction, you can drop this two and you get dy dx. And the same thing here, whatever it is here, you can drop it. You can go back to dl dt. And so all you have to figure out, what do we need to put here? Look at the length. Length is a function of what variable? W. Therefore, you need dl dw, which means you're going to take the derivative of this one with respect to w, and then dw dt, which means you're going to differentiate this one with respect to t. If we want to go with the Leibniz's notation, and it's a very simple process. So dl dw, take a look at this one. You want to differentiate this. So 0.25 remains, 2.6 becomes a coefficient, and w to the power of 2.6 minus 1, or 1.6. So dl dw is this part. What is dw dt? I hope you see that it's very simple. Take the derivative of w with respect to t, and it becomes 0.21. Now, if I multiply this number, and this number, I get the following. Now, I have two choices. I can replace the w with this. If they ask what is dl dt as a function of t, I must. But if they don't, and they just want the answer, since at t equals 100, I know w is 24, I'm going to replace it, use a calculator, and come up with the answer, 22.0532. In general, as far as the number of decimals, you want to carry a lot of decimals. Although these are all estimates, most of the time they ask you for a specific number of decimals. But why the unit is millimeters per day? Look at this one. dl, change in length, over dt, change in time, millimeters per day. Okay. So we should be able to figure out the units from here. Now, this is simple enough. We can do the second method, meaning we can find L as a function of t by replacing w with 3 plus 0.21t. So here's the second method. You don't have to do both methods, but I want you to be exposed to both. So part A, how long is the tiger when it's 100 days old? Replace this with 100. And now, of course, use a calculator. And when you do that, you get exactly the same answer that we had in the first place. But again, you have the composite function of L O W in essence. This becomes L of t. Part B, we are going to differentiate this expression. I hope you see 0.25 remains times 2.6 times the same thing to the power of 1.6 by the chain rule times 0.21. So again, 0.25 remains, 2.6 becomes a coefficient, the parentheses to the power of 2.6 minus 1 by the chain rule times the derivative of 0.21. So we are using the extended power rule on this in essence. And if you multiply this number, and this number, you basically get the same number that you had here. And now you can replace the t with whatever number they gave you, in this case 100, and the number you get, it better be the same as this one, and of course it's the same unit. As you can see, both ways are possible. The difference is not huge, and if you find one is easier than the other, so be it. But in some instances, it's not as easy. So here's another example that I believe we better stick with the methodology of Leibniz notation. Could somebody read this one, please?
The amount of glass recycled in a community is G of P equals the square root of 0.5 times P squared plus 7 tons, where P is the population in thousands. It is estimated that T years from now, the population of the community will be P of T equals 4.4 plus 0.1 times T squared 1,000. How many tons of glass are expected to be recycled 4 years from now? And find the rate at which the amount of glass recycled is changing with respect to time 4 years from now.
Excellent. Thank you so much. So pretty much the same as this, the previous one. G is a function of a P, so the intermediate variable is P. P is a function of T or time, and we want to find how many tons of glass are expected to be recycled in 4 years. So we're going to replace the T with 4. That's 16. This is 1.6. And they add up to number 6. And that's 1,000 people. Now we're going to put this into G of a P function. And this square root class, this is 36. Half of it is 18. With 7 becomes square root of 25, which is 5. 5 what? Tons of glass. This is where the units come from. Part B, find the rate at which the amount of glass recycled is changing with respect to time 4 years from now. Now, it's important to see again, one point in time, the word rate means instantaneous, means differentiation. So the rate of what? G with respect to T, so dg dt. So glass, time, dg dt. And I'm going to go again with this one, and I'm going to write dg dt, and we're going to figure out what we need here. Going back to this dy dx is dy du du dx. Du is the intermediate variable that connects the y to x. So what is the intermediate variable that connects the g to t? It's p. So dg dp dp dt. So we're going to find this one and then this one, and we multiply them. To find dg dp, that means you want to differentiate this with respect to p. And as you recall, we have to rewrite this as 0.5 p squared plus 7 to the power of 1/2. So we'll be able to use the extended power rule. So we're going to differentiate this one, and that gives us dg dp. So 1/2 sits in front. 0.5 p squared plus 7 to the power of 1/2 minus 1 makes it negative 1/2. By the chain rule, the derivative of the inside, which is 0.5 times 2p, or simply p. So I'm going to quickly, I'm going to discuss this. You don't have to worry about it now, but quickly, 1/2, same thing to the power of 1/2 minus 1. And how do we get this? The derivative of the inside, 0.5 times 2p. Let me just write this here. So this one is the product of 0.5 and 2p. Then we want dp dt. dp dt is 0.1 times 2t. 0.1 times 2t or 0.2t. So what can we do? We have two choices. I can replace this p and this p with this function and plug in t equals 4. However, since they just want the answer and they didn't ask for dg dt as a function of t, again, if they ask for dg dt as a function of t, you must replace this p as well as this p with 4.4 plus 0.1 t squared. So you have to work on that. The reason we don't have to, because they didn't ask. So what is t? We know t is 4. But what is p? When t was 4, we found the p to be 6. So replace the p with number 6 and t with number 4, evaluate it. So we're going to plug in. We're going to plug in p and t. P and t. So I hope you remember this part is the same as this part. So this is 25, right? Because this is 36, half of it is 18 and 7, 25 to the power of negative 1/5. So this one is 25 to the power of negative 1/2, which makes it 1 over the square root of 25, which makes it 1/5. So we have 1/2 here, 1/5 here, 6 here, and these two, the product is 0.8. So the first number remains. This one, we showed that it's 1/5. This one doesn't go away. And these two, the product is 0.8. If you multiply everything, you get 0.48 tons of glass per year. Why is this the unit? Take a look at this one, dg dt, the units of the change in g over change in t, tons of glass over here. Now, if we wanted to do it by composite function, you have to replace the p with 4.4 plus 0.1 t squared, and this probably is a tad longer to differentiate, okay? But it can be done. You can try it at home, and you'll be fine. Let's continue. We want to differentiate cosine to the power of 10 of sine x cubed. So there is a lot of chain rule involved. And some people like to write ddx of this, ddx of that, and it becomes very confusing. I want to show you an easy way to come up with the answer. So number one, notice this means cosine to the power of 10, which means right here, ignore what you have here. Whatever it is, the power of 10, you have to use the extended power rule. So first, 10, then the same thing to the power of 9. So n, g of x to the power of n minus 1. This whole thing, think of this as g of x. Think of this as g of x. So 10, g of x to the power of 9. So that's the first part. 10, g of x to the power of 9. So 10 cosine to the power of 9 sine x cubed. Now what do you want to do? You want to differentiate cosine of sine x cubed. So let me write this. I want to make sure everybody can see that we have now cosine, and I'm going to stop. So what is the derivative of cosine? Negative sine, everybody. Now I'm looking at this one. I want to differentiate. What is the derivative of cosine? Remember, the way I'm going to read it, I'm going to read cosine and I'm going to pause, which means my main function now is cosine. So negative sine. But negative sine of what? The same thing. Negative sine of the same thing. So cosine of the sine x cubed gives you minus sine of x cubed. And then the derivative of sine of x cubed. So now you are looking at this part. So let me write it as a sine x cubed. I want to differentiate. So let me be clear as to what's going to happen. So I'm going to read sine. The derivative is cosine. Cosine of what? Whatever you have here, cosine of x cubed. And then x cubed gives you 3x squared. If you do it this way, you will never, ever make a mistake. I highly recommend you go over the recording to see what I've done here, and you can easily see the answer. So now we are done with calculus. We are going just going to rewrite it properly, okay? So 3x squared and 10 and negative sign, 10, negative sign and 3x squared is negative 30x squared. Cosine of x cubed, and then we have these two pieces. So 10, let me just make sure everybody understands where. So this one, the sine, and this one give us this one, okay? Then you have cosine of x cubed, cosine to the power of 9 of sine x cubed, then sine of sine x cubed. Whether you put this one first or that one first, it doesn't matter. You need a raised dot in between. But I want to make sure we understand how we combine these three pieces, and we put it in front. So that's the chain rule. We're going to move on. We want to differentiate this. The very first thing we do, we put a raised dot in between. And now we use the product rule. F prime G. So what is F prime? So we are looking at the product rule now. F prime is 4x cubed times G e to the power of 2x. So F prime G plus G prime. What is the derivative of e to the power of 2x? Well, any exponential, the answer is itself. And then times 2. And then times f x to the power of 4. In other words, this is f prime g plus g prime f. And all you have to do, factor out the common factor of 2x cubed e to the power of 2x. I hope you see that 2 is in common between 4 and 2, x cubed between x cubed and x to the power of 4, and e to the power of 2x. So this is in common. What do we put here? Divide this one by this one, and it just gives you 2. Divide this one by this one, and it gives you x. I'm hoping nobody has any problem with the factor. I want to differentiate this. One thing I want to make a point of, if this number is involved, number 9, in other words, if it's 9,000, if it's 1.258, or if it's 2/3, so it makes it involved, you can put a bracket here and just differentiate, use the product rule on these two pieces and multiply everything by this number. Since it's not a big deal, you can think of this as f. this as G. Again, you could write this with brackets and just keep the 9 times everything, okay? Because ultimately you have to factor it. I want you to know that. In this case, really doesn't make that much of a difference. So we are going to go with the product rule F prime G. So this is 9 times x minus 1 to the power of 4 plus G prime. So how do we differentiate this? 4 times x minus 1, 4 times x minus 1 cubed times the derivative of the inside happened to be 1. So I write it on purpose. And finally, G prime F 9x. So again, let me write at top of it what we have here. So we have F prime G prime F. And we are done. Right here, we are done with calculus. Now, we notice 9 is in common, x minus 1 is in common, and which one do we use, exponent 4 or 3? Exponent 3, because it's a simple factoring. So from this first one, we just get x minus 1. When you divide this one by this one, it just gives you x minus 1. When you divide this one by this one, it gives you 4 and x, because x minus 1 cubed goes away, 9 goes away. And so if you combine x and 4x, you get 5x. So the final answer is 9 times x minus 1 cubed times 5x minus 1. That's the final answer. I'm going to differentiate y equals sine squared 8x. It may be helpful to write this as sine of 8x to the second power. Again, you don't have to write it in this fashion, but if it helps, by all means. And so we're going to start with the extended power rule. So 2 sine 8x to the power of 1. And then all you have to do, the derivative of sine 8x. And remember what I told you, if you're dealing with a sinusoidal function, just read sine and stop. The derivative of sine is cosine. So cosine of whatever the argument is, sine gives you cosine of 8x, and then 8x gives you 8, and we just rewrite it by multiplying these two pieces as 16 sine 8x cosine 8x. All right. I want to differentiate this, and that uses the product rule. F times G. So we're going to use this product rule, which is F prime G plus G prime F. So F prime is 3 times 3 to the power of x plus G prime F. So let's start with G. The moment you see an exponential, the answer is itself. Is the base E? No. So by logarithmic properties, ln 3, in essence, we are looking at this one, okay? And then going back to the product rule, G prime F, so times F, 3x. So I'm going to write at top of it F prime G G prime F. And we're going to combine things. We notice this is 3 to the power of 1. We know this is, let me use a different color. This is 3 to the power of 1. This is 3 to the power of 1. So these two combine into 3 to the power of x plus 1. And so these two. So this is 3 to the power of x plus 1. The second one is also 3 to the power of x plus 1 times ln 3 times x. Again, these two will result in 3 to the power of x plus 1. So if you factor of the common factor of 3 to the power of x plus 1, it gives us 1 plus ln 3 times x. We write it as x ln 3. Again, the reason we do, because if you put the x here, one may read it as ln of 3x. We don't want that. We put the x in front. The next topic we're going to look at is implicit differentiation. Functions expressed by one variable are defined explicitly in terms of another variable. For example, y equals f of x in general, y equals x squared minus 2x plus 1. Those are the functions we have been dealing with. However, some functions are defined implicitly by a relation between x and y, such as x squared and y squared, they add up to 25, or x cubed plus y cubed equals 6xy. And in some cases, it may be difficult or even impossible. In some cases, it is possible to solve such an equation for y, and in some cases, it's not easy to do so. In some cases, may be completely impossible. That's why we look at what's known as implicit differentiation. So we're going to look at an example as a warm-up example to see how we do it both ways. So if we have 4x plus 2y equals 10, it's a very simple example. We can differentiate it explicitly because we can solve for y. I hope everybody can see we can move the 4x. We can move the 4x and we can divide by 2. So again, if you want, we can write 2y equals minus 4x plus 10. And if you divide by 2, you get minus 2x plus 5. And clearly y prime is negative 2. It's very simple. But as you can see, it was easy to solve for y. But could we have done it implicitly? And the reason we want to do that, because in case it cannot be done, or we don't want to do that for any reason. Well, in that case, here's how we do that. For x, the derivative is 4. 2y, it's important to know y is like g of x. Okay, let's in fact write it in this fashion. Y is the same as g of x. So when you differentiate y prime is like g prime of x, meaning 2y, the derivative is 2y prime, or dy dx. Another notation would be dy dx. And clearly, I can move the 4 and make it negative 4 and divide by 2, and I get to the same answer. So on purpose, by the way, I put one of them as y prime, one of them as dy dx, just to remind you they are the same. And this was easy enough to see, okay, both ways will do the job, okay? And in some cases, it's not possible to solve for y. So in this case, we could solve y explicitly as a function of x, and we did that. In some cases, we can't. So for example, 2x plus y to the power 4 equals x minus 2y. We are going to differentiate it using implicit differentiation. So let's see what we do. Something to the power of 4. I hope you see that we use the extended power rule. So 4 times the same thing to the power of 3. So extended power rule. I'm looking at the left side. And according to that, we need the derivative of the inside. So again, 4 2x plus y cubed. Now, what is the derivative of the inside by the chain rule? This gives you 2. This gives you y prime or dy dx. And again, on purpose, instead of dy dx, I'm going to write y prime because I want you to see they are interchangeable. They are the same. Okay. In fact, this tells you the independent variable is x. So you want to be careful because this is more precise in essence than y prime. What about the right side? X gives you 1 minus 2, y gives you y prime or dy dx. Since we use y prime here, we're going to use y prime here. So I'm going to quickly recap. 4 becomes the coefficient, the same thing to the power of 3. And this is by the chain rule, everybody. The derivative of the parentheses is 2 plus y prime. The right side, x gives you 1 minus 2y gives you minus 2y prime. And this is the only calculus step. Everything else from here is algebraic step to solve for y prime. So you can use various types of methodology that you've learned to solve for y prime. It's absolutely up to you. But one easy way, just the way it is, I can distribute the 2 by this, and I can distribute the y prime by this on the left side and keep the right side intact. So 2 times this, and I'm going to write it in green, and y prime times this, and I'm going to write it in red on purpose because these are all algebraic steps. Remember what we are solving for, dy dx or y prime. So anything involving y prime must come together. So meaning this moves to this side, becomes plus 2y prime. This moves to the right and it becomes negative. This one plus this one minus. So all you have to do, factor out the y prime and divide by. So if I factor out the y prime, it gives me the blue piece here. And from the red, I get the 2 only. So I'm factoring. It's all algebraic steps. And again, let me just put an asterisk next to this was the only calculus step. So now all you have to do, divide by the brackets, both sides, divide by the brackets, and that's y prime or dy dx. The right side, 1 minus 8 times 2x plus y quantity cubed over the brackets, 4 times 2x plus y cubed plus 2. This is implicit differentiation. We're going to practice a little bit more. All right, we are going to continue with the implicit differentiation. In the case of sine y plus 2x cubed y squared equals 6. And we're going to start with sine y. And again, I'm going to put sine and I'm going to stop. The answer is cosine. Cosine of what? Y. Is this x? No. This is y or g of x. Therefore, times y prime or dy dx. So let's make sure everybody understands what happens. Sine gives you cosine. You write the same argument, whatever it is. By the chain rule, the derivative of the argument y is dy dx or y prime. Now we're going to move to the second piece, and I'm going to put a raised dot in between. And I want to show you this is f, this is g, and you're using the product rule on that. So 2x cubed gives you 6x squared times y squared plus, now y squared gives you 2y, y prime, or 2y dy dx times 2x cubed. So, and any number gives you 0. So let me write this. So this one is f prime g plus g prime f, and this is the only calculus step. All right. The next step is to solve for dy dx. Everything involves dy dx except this piece, so you're going to move this to the right. So 6x squared y squared, we want to get rid of. But before we do that, let's see what we can simplify. This one and this one we can combine into 4x cubed y. We could have done it in one shot. So 4x cubed y dy dx. And now this moves becomes negative on the other side. And the other two pieces, we take the common factor of dy dx. By the way, we are interested in dy dx. Even if there are other factors, you can take them out, but most importantly is dy dx. So all we have to do, divide both sides by cosine y plus 4x cubed y. So divide both sides by this expression, and it gives you y prime or dy dx, and we are done. So implicit differentiation. Again, this is the calculus step we should be comfortable with. The rest is fairly simple. It's all algebraic steps that you have to take afterwards. Find an equation of a tangent line for the function at 0, 1, x e to the power of y plus y e to the power of x equals 1, and it requires differentiation by implicit differentiation. So to differentiate that, let's put a raised dot here first, and then we look at the second piece. So you're looking at the product rule. F prime is 1 times g. So we are looking at so f prime is 1 times g e to the power of y plus g prime. When you look at the exponential, it's always itself, e to the power of y. And y, it's like g of x, remember that. So by the chain rule times y prime, and then times f, which is x. So this would be f prime g, g prime f. Now, we're going to put a raised dot. Let me use a different color here. We're going to put a raised dot here. And now we're going to call this one fg. And we're going to use the product rule on those. Y, so we are looking at f prime g plus g prime f. So f prime is y prime or dy dx times g or e to the power of x plus g prime f, the derivative of e to the power of x is e to the power of x times y, and the number gives you 0. E to the power of x times y, and the number gives you 0. So let me write this in green so you can see. In essence, you're dealing with f prime g plus g prime f, and we are done. All we have to do, solve for y prime, and then we have to plug in to find the slope. So let's clean up. We are going to see that anything involving y prime we can keep, and these two can move. So we're going to keep this on the same side. We're going to move this, becomes negative e to the power of y. This becomes negative e to the power of x times y, or you can put it as a plus and negative in front of a parentheses. So I hope everybody can see that basically we moved this one and this one, both of them have a negative sign. And so all you have to do, divide both sides by the parentheses here. Now this is y prime. So I want to make sure everybody understands. If you want to find the equation of any line, you need two things. You need a pair which is given, and you need the slope. Is this the slope? No. This is the derivative function, which represents the slope of infinitely many tangent lines. What about the tangent line at this point? Then you plug in 0 if it was just the explicit function of x. But since it's an implicit function, you replace the y with 1, x with 0. That's the meaning of this. So class, we have minus e to the power of 1 is e, plus e to the power of x, which is 0, it's 1, times y, which is 1. So if I were to write this, I would put e to the power of 1, and we have a negative sign. So negative fraction for e to the power of 1 plus e to the power of 0 times 1. Then we have e to the power of y x e to the power of 1 times x, which is 0, plus e to the power of x, or e to the power of 0. So all you have to simplify this, and I hope you see the numerator is e plus 1, the denominator is 1, and the negative sign in front doesn't go away. So it's minus e minus 1. And now, since this is 0b, this is the y-intercept, you can use y equals mx plus b, meaning this times x plus b, and b is 1, everybody. So this one times x plus 1, and you can keep it like that because the slope is minus e minus 1. And the reason we keep it as e, because it's an exact answer, and in calculus, we rather keep it as exact.